we all are here, and maybe recordings will be not needed. Who is Fermi?
I know the Fermi lab is named after him, but that's it.
Anyone knows who was Fermi? Okay, what's ethnic background, just based on the name? Huh? No, ethnic background. Mathematician is more like unifying. Huh? Close, a little more to the south.
Enrico Fermi was an Italian-American physicist in the early 20th century.
Okay, yeah, thank you, Steven. So he migrated from Italy to the United States. He did the first operating nuclear reactor, and he was basically dealing with nuclear physics, but he left, and he was doing experiments. But in addition, he left, how to say, a wisdom, a prescription for theorists, what to do if they want to achieve results very quickly. So Fermi's golden rule is replacing like several pages of calculations. It is a shortcut, like a hint from experimentalist to a theorist. And it teaches us how to find a rate of a process. So it can be applied also to chemical processes like reaction rates, but now we will think mostly of rate of how quickly molecules are being excited. Like if you have ensemble of Avogadro number of molecules, and we have certain amount of time, which proportion of these molecules will be excited if we irradiate it with so long time or longer. So how this intensity, how this rate of excitation will define number of excited molecules. So his prescription is as follows. One takes the matrix element of interaction squared and multiplies it onto density of final states. Like if there are more products than reactants, it will go quicker, right? Because there are several pathways. And there are some factors. So we are going to practice this Fermi golden rule in a sense that it shows what to do with the matrix element that we have just discussed, right? So here we will put our matrix element of interaction or electric field times matrix element of transition dipole squared. Okay. So I'm going to show a few more ugliest slides in today, but before we try to look on equations, I'll try to explain it by lay language. What is the goal? So we want to merge together wave function of initial state, wave function of final state, and operator. Our wave functions are quite complicated, not because just quantum mechanics is complicated. They're specifically complicated because they are functions of more than one variable, which is always a big pain. So if you took any PChem quantum course in the past, if you will take any in the future, you will notice that basic core of such courses deal with only one variable, maximum three because of 3 dimensions, like hydrogen atom. Here we have independent variables of different nature, electrons and ions. And this is objective complication, even for people who already deal with quantum theory for a long time. So before going forward to practically find this intensity of interaction, I do want to practically implement factorization of electronic and nuclear wave functions. And on this way, I'm going to use a concept of basis functions. Did we discuss in our past meetings in the form of interview? Did we? Basis, right? In mathematical sense. I think Lola did ask this question, and I was, to address her question, I was drawing Taylor series on the board. Was it in this class or different class? Oh, a different one. But everyone is happy about basis, right? Okay, I'll go through main core and then we'll go to questions. Amount of questions that may arise during today's meeting is more than can be answered during this meeting. So basically, the rest of the course will be answers to the, you may write down questions. Okay. So I'm not sure if I can pass through this barrier. Please confirm if you're happy with concept of basis states, or absolutely not happy, or more or less. Just confirm. It's okay. 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 Lola needs to sum up. We discussed it, right? Down. Okay. Middle. Okay. So I put in danger everything we do, but there is no reason to go forward without a little of basics. So I'm going to insert one more slide in between. Insert blank slide. Okay. So I will not ask you if you're happy with Taylor expansion. You should, right? So any function in the vicinity of a point can be approximated as so x approximately x naught, a value of the central point plus first derivative, or we can write df dx in the point x naught times x minus x naught plus d second dx squared of f in the x naught times x minus x naught squared plus so forth. Did you saw it before? Right? So it's please confirm. Okay, so it's Taylor expansion, and it is in some schools. It's either beginning of the calculus at college or very end of high school math. So here is the idea that we represent our general any function as a summation of the polynomial function. So we can say it is equal, and this term can be written as x minus x naught to the power 0. So then we will write that any function can be represented as summation some coefficients times x minus x naught to the power n, right? So one function is represented as infinite summation of other functions. And these other functions are called bases. So it's a very standard mathematical tool. And polynomial functions may or may not be good in specific circumstances. There are some engineering and natural science applications when polynomials fail. So more generally, one is telling that it is just summation, coefficients, and then some basis functions. I can use letter phi typical in quantum theory, but here I'm telling just anything. So set of basis functions, and we, or whoever applies this concept of basis functions, needs to be sure that the basis is complete, that there are enough basis functions that will have wings far away to represent any function, and that it will have fringes or different curvatures to be general, right? Okay. Please confirm if it was okay. Now, going back to the slide where I was not comfortable. We are planning to represent our combined wave function of molecule as a product of electronic and nuclear part. And each electronic and nuclear part needs to be expanded in the basis. Why? Why we do it? Not because we really want to like celebrate basis day. There are mathematical benefits. Even if we do not know these basis functions, if they will be found later, we can practice some operations and we can make prescriptions what to do with functions, even if we do not know them now, but we will know them in the future. And we can be very, how to say, meticulous, rigorous, and have a practical protocol what to do. So for electronic functions, it will be a summation of all basis functions and expansion coefficients. And just to make our life simpler, we will assume that there is only ground state, excited state, and then coefficients will be C, G, and CE, right? Simple basis. Those of you who do quantum chemistry for profit typically deal with much bigger bases and more states. Here we are humble. Now for nuclear part, I will keep using uppercase indices for nuclei, so infinite number of states, basis functions which are appropriate for quantum nuclear oscillations and expansion coefficients. So here I'm putting a little bookmark for the future. The specific, we will briefly cover today, but specific shape of eigenfunctions for molecular vibrations in this parabolic potential is something that we will need to cover as your basic background, and something that will be, I'm sure, used for next part of the course. So you will see quickly some of these functions, and later on we probably need to put a little bit more focus on it. So why this slide is presented? Because instead of Dirac notation or explicit algebraic notation, I'm going to use this basis notation. And it is not a unique tool for this problem and for today's class. Basis notation is used elsewhere. And if you want a little bit more, basis notation is a key to make conversion from continuous variables to vectors and back. Because these functions are continuous here and there, and expansion coefficients just discrete set of vectors, and they mutually replace each other. Okay. So this is not a derivation slide, it's more a summary slide, just to stop in between and look around where we are and what are we doing. On the top, I'm giving the pairs of basis functions. So one pair, another pair. First term in the pair is electronic, second is nuclear. And this is initial wave function. and second one is final. So we are looking for transitions between these pairs of function, or the initial function and final, each of which is replaced as a pair. Why we are doing and what is the goal? We are going to compute, calculate, discuss in matrix element of transition, then take a square of it and apply Fermi's golden rule, right? So on this way, we also need to take into account some other details. Each of the function can be labeled by this uppercase and lowercase index, right? If you say that our molecule is not in infinitely long superposition, but exactly in the eigenstate, both in respect to electronic and nuclear degrees of freedom, then instead of infinite sum, we have just two indices, one index for electronic state, another for nuclear state. And then we can tell that we are going to make transition from lowercase m uppercase m to lowercase n uppercase n, right? So from one function to another. If we are doing this transition, we also may take into account that each eigenfunction, has its own energy. And if this pair, the product of electronic and nuclear wave function, has its energies, then the energies will be also labeled by two indices, electronic index and nuclear index. So energy lowercase m uppercase m, energy lowercase n uppercase n. And the subtraction of these two energies must match the energy of transition, the frequency of photon, if we want it to be practical, if we want any reaction of photoexcitation. In chemical sense, photoexcitation is not reaction, but who knows, everything is general process of photoexcitation, right? Now, the next line is specific implementation of Fermi's golden rule for this specific problem. So Fermi taught us that the rate of a process is interaction matrix element squared times density of final states, right? So the interaction energy squared in notation of spectroscopists is referred to as oscillator strength. So basically it's interaction energy with factors. Since we are considering transition from lowercase m uppercase m to lowercase n uppercase n, this oscillator strength has four indices, right? So two indices for initial, two indices for final. And then for density of final states, we do have this delta function, which I think we covered a couple of meetings ago, right? So it will be infinitely high if argument in brackets will be zero. So basically, if transition energy, if energy of photon is exactly equal to the energy of set of states. So we have two factors in order for photoexcitation to happen. We need resonance condition and we need favorable oscillator strength. And oscillator strength is very close with precision up to a factor to transition dipole matrix element squared. Okay. Please write your questions. If you would do standard style with interview, probably we would finish class right now. I'm sure there are questions, or just list concepts that seems new or not quite understandable. I'll try to collect this information and cover. Okay. So if I want to process resonance condition, I need to subtract energies of initial and final state. And here is one of the equations that we need to cover later on, and the one of the equations that definitely will be used in your next class. So let me make a little circle here. If any of you is doing Raman or FTIR, infrared spectroscopy, you may seen it, and you may seen it in other courses. So the energy of our combined electronic to nuclear state is consisting of energy of electronic state plus energy of vibrations, right? Energy of electronic state is just one, E sub m, which can be either found from experiment or computed by quantum chemistry. The energy of vibrations has a regularity. So if it is only one interatomic mode, one vibrational mode, we know its frequency, and then this quantum number stands for how much heat, how much energy of oscillations is stored in a given mode. Since it is quantized, it cannot change continuously. It is changed in a discrete way. And vibrations can exist only in the quantum states, where their energies offset from each other by the energy corresponding to frequency of vibrations. So this equation that you'll definitely go over and that you need in other class is energy of eigenstate of a harmonic oscillator. Just a little side note, why energies are important for the next part of the class. In the next part of the class, one would play with Boltzmann distribution and statistical sums, where probability for certain configuration to exist, to be observed in a nature, will be e to the power energy of the state divided by kT. And if we and there will be some summations, some denominator. It's not my part, not my business to tell about you, but the energies of quantum states here will be imported from this part of the class to the next part of the class. And this energy of harmonic oscillator will be used there. I don't know if there will be homeworks to solve or just to observe. So you will see this equation many times. Oh, and probably you have seen it before. Now, if you subtract these two things, so we subtract energy of electronic levels and we subtract energy of oscillations. If you speak only about two electronic levels, it will be like excited minus ground, just one number. It's same as in hydrogen atom. For two electronic states, there is a very narrow line, right? Only one transition. But if it is a molecule, there are several additional transitions because of this quantization. And energy of transitions will be equal to subtraction of the vibrational quantum numbers. Good. So if we are practicing transition from this vibronic states for vibrational and electronic, right? From this vibronic state to this vibronic state, here is the energy of transition. Okay. And I'm still pursuing a goal to find the energy, matrix element of energy of interaction. And we know that I can factorize it by putting intensity of electric field away. So I'm trying to simplify this consideration and make it less general. Typically, molecules have a lot of nuclear vibrations. Anything except diatomic has several, right? Any molecule has a lot of electrons. So typically it is integral over more than one nuclear, integral over more than one electronic, and these functions are more complicated. Here, just to save, if you're not taking notes to save my effort on showing, if you're taking notes to show your effort to rewriting things, I try to make things condensed. So ground excited interaction. As we go through this procedure, I'm going to use no, I'll talk about a little trick later. So it is the same thing everything is good. I know the trick that I'm going to apply, and I will talk about it. So this is our goal. This matrix element squared will define the intensity in the table and define the figures on the backside of this form. What needs to be taken care of right away? Due to temperature effect, due to we assume that the experiment is done at low temperatures, which are smaller than vibrational frequency, we assume there is no thermal population in the ground state. So we will consider only ground vibrational wave function. It will make things easier, and it works in most experiments. Another thing, if we are well-developed quantum theorists and mathematicians, we can find a little inconsistency. So left and right part depend on both electronic and nuclear, and operator does work only on electronic thing. There is inconsistency. There should be also dependence on nuclear degree, but there is no dependence on nucleus. So there should be a mathematical trick. Everywhere one should have dependency, but one doesn't have, one can plug in an identity operator. So in terms of matrices, matrix where there are ones on the main diagonal. And here we will symbolize unity operator in respect to nuclear coordinates. Okay, so here, do you want me to stay longer on the previous slide, or is it okay to go forward? Okay, so here are the immediate consequences, positive consequences of this trick. So normal people do not like to take double integrals or take integrals at all. But at least if it has to be done, it's better to use the principle of ancient Rome, divide and conquer, right? To take one integral first, second. So if we have this trick of unity operator, we can identify that there are things that depend. Let me correct a quick typo. Here should be lowercase. We can factorize the integral in such way, I can even rewrite it. M ground chi n integral dr capital. So on the what I sketched in the upper line, it was what we had on the previous slide, right? And now I'm doing the following trick. Hocus pocus. 1, 2, 3, maybe 4. And now with wavy lines. 1, 2, 3, 4. So I'm changing the order of the factors and combine everything that explicitly depends on position of electrons here and combine it with integral over position of electron. So this equation, first integral, is completely independent on what nuclei are doing. In second part, we have integral over positions of nucleus, nuclear wave function, nuclear operation, nuclear wave function. This is another self-contained integral that we can process independent of what electrons are doing. I don't know if it will bring us to any scientific discoveries, but it's definitely simplifies our life as mathematicians, or simplifies a life of mathematicians who need to solve this problem. So why we spend time on this problem? What is the goal and consequences? Are there positive consequences? Are we just drying young brain with heavy problems for general education, or there are practical benefits? These integrals are simple enough, and the goal, I don't know if I described it, and it is not a good style to declare a goal closer to the end, but the goal is to find these intensities as functions only of these quantum numbers. Or one can make connection and make this intensity as function of transition energy, right? If we will find the intensities as function of transition energies, then we will be able to plot spectra, right? So, and I will show slides to achieve this goal. So hopefully, if we do everything correctly, the result will not depend on positions of electrons, will not depend on positions of nucleus. It will depend only on the factor m, on the quantum number m. So going from ground to excited, going from chi n equals 0, ground state, and then we go to different excited states, each of which have different lengths of the arrow, which means different transition energies. And we are looking to find how the intensity of transitions depend on the number of this vibrational state. And whenever needed, we will use offset of their equilibrium as a parameter. Okay. There is a trick. I invite another, so it's in some sense our today's meeting is like combination of tricks. And I will try to improve and do a little slower style with interview. I just need to rush through. Another trick, which is also quite advanced. So it deals with concept of basis decomposition, of expressing one function in the basis of set of others. And here this equation and specifically these little factors tell that the ground vibrational state, ground wave function of the ground vibrational wave function can be expressed in the basis of eigenfunctions of the excited parabola, of excited potential energy surface with certain coefficients. So if we know these functions, and we will know them in like a couple of weeks, one can find the overlap of ground and excited state parabolas and find that their overlap is well-defined analytical function. So this function decreases as index m increases as a square root of factorial of this number. And it increases as power m, or alpha in power m, where alpha is proportional to offset of these parabolas in coordinate. So this equation, I'll just jump back one slide. This equation tells that the field function can be expressed as sum of these empty functions with certain coefficients. So this discovery, these coefficients, was awarded by Nobel Prize to the scientist Roy Glauber. And the name of this trick refers to the word of coherent states. And it was done much later than original concept of Frank Condon factors that we are covering today was designed. Okay. So we are not deriving this in this class. We are taking as a given input, and it comes from the concept of coherent states that we cannot cover. Just use this equation. So we agreed that this thing is a product of two factors. One electronic, which is the same for as long as we have the same ground electronic and ground and excited electronic. So we can consider it as a factor, times the vibrational integral, right? Where we place this unity operator in respect to vibrational frequencies. So if we plug in a trick of coherent states into attempt of finding this overlap of ground and excited vibrational states, we will find that functions will cancel and we will have this factor there. So interaction matrix element of interaction is a factor of electronic part, which is not changed, and nuclear part, which is often referred to as FCF, which stands for Frank Condon factor. So those are two scientists who realized almost everything we do today right 1 year after design of a Schrödinger equation. So it was designed in 1927, and it is the concept of this Frank Condon factors explanation why vibrational spectra has this substructure was used for like a century for interpreting experimental spectra. So even if we cannot do calculations, we can see these Frank Condon features in experiment and explain where they're coming from. So to practice this factor, I suggest a couple of numerical values. So the parameter alpha, which is proportional to offset, in fact, it is offset of coordinate multiplied by these factors: mass of vibration, frequency of vibration, Planck constant. Here are typical values, like if we deal with carbon, then it is 12 times mass of proton. In atomic units, it will be about 24,000. If we are looking for typical stretch in the infrared spectra, it's what, 1,500 inverse centimeters, which is about 2.3 electron volts. We will take as an example a little smaller, like 0.1 electron volt, which is quite typical for vibrations. And in atomic units, it will be about this number. And the interatomic distance, just for this example, will be set up as like about a quarter of atomic unit. Atomic unit is the distance between proton and electron in ground state of hydrogen atom. And it's about half of angstrom. And here, if atomic unit is half of angstrom, it will be about 1/8 of an angstrom. It's quite big oscillation. So if you plug these numbers here, we can get this alpha factor and use it into the Roy-Glauber equation for coherent states. In fact, I made up these numbers to get number 2 here to make your calculations easier. My pleasure. So now we are getting to your table. So in first column, we just put the numbers. So from ground to ground, from ground to first, from ground to second, from ground to third, and so forth. Now we place energy offset. So I don't remember what we agreed on delta E, but here we put 0 times vibrational frequency. And here I just progress plus 1, 2, 3. And later on, these values will be used as an argument for the image. And now my main task is to compute these factors, which will be responsible for intensity of light absorption, using the plugging in number 2 else everywhere where we have alpha. So I put E to the -4, 2 times in the power 4, 2 4. Oh no, in we have alpha in times 2, 0. So it will be 1 divided by factor of 0 will be 1, right? So it will be E to the -4. And E is about 3, a little less. So 1/3 into the power 4. So very approximately 1/3 power 4. So about 1/81. Very roughly, you can compute it better. And please do it on your own. I will do same as people do in culinary show, where the person in front of camera does some operations and then takes a bowl with ready thing. And okay, here we arrive. Yeah. So here what I did one of the previous years, you can compute it a little more precisely. But what is interesting in these numbers, so this factor e to the minus 4 is the same, and the rest of the factors, they increase and then start decreasing, right? And it originates from the fact that we have competition between power function in the numerator and the factorial functions in the denominator, right? So what do we do next after these numbers are ready? Again, my images are not a good example to follow, but basically I take the number from a table and put it on the heights for the first number. Then I take the number from the table in here and put it there. So I'm trying to progress and put all numbers, and then I need to explain why there are these fingers. So it is another concept that we're not going to provide equations just verbally. In addition to degrees of freedom that we have considered explicitly, there are other degrees of freedom. For example, there are collisions of molecules, there are rotations, there are signals coming from different molecules in an ensemble. So there are additional factors that are not leading, but existing, and we cannot take them into account at once. Maybe there are some other vibrations that we skipped because here we used only one vibration. And all of these factors bring so-called homogeneous and inhomogeneous broadening. They tell that our resonance condition doesn't need to be matched literally. Transition will be available, will be possible, even if light frequency is a little bit less or a little bit more than the one that we predict by our theory. And instead of doing rigorous theories for widths of these individual peaks, sometimes people just use as a factor of temperature, of thermal quantum. The higher the temperature, the bigger the width. It's like rule of thumb for a quick fix. If one really needs exact value, then there are advanced theories which are really cool, but no time now. So please try to build this figure based on your calculation of this equation. I'm going to collect them. Do we need to finish at 12:30, right? Okay, so here is a little summary of what we did. So I think it is what we started last Monday, right? From this figure. And here you have a little bit better idea of what these numbers are, what these indices are. From ground to excited, 0, 0 transition. From ground to excited, 0, 1 transition. And here are the shapes that you did yourself, right? I think one can put a little arrow and show that here we are coming from ground state in blue surface into ground state of red surface. And the intensity corresponds to overlap, how much this peak overlaps in space with this one, right? So it will be a little area here, this overlap. If you go to the next one, we overlap ground state here and first excited state is there. So the overlap will be there. And you see, since this little peak is closer, they have bigger overlap and the peak is taller. When we come here, this ground state peak and the 1/3 of the second excited state are almost above each other. Therefore, it has maximal intensity. And if you go further, it's also big, but it already moves away. And if you go further, our center of the ground state peak is in between of other peaks, therefore it declines. And also, if you go further, its probability in excited state is smeared over so many sub-peaks, and we have overlap only with few of them. Therefore, it keeps declining. But if one pulls out experiment of real molecule of many natures, metal organic complex, pure organic, just in the right wavelengths, this Frank Condon substructure is quite universal. So it's not only for the course, it's for practical spectroscopy. This eigenstates of harmonic oscillator is something that one would need as a background knowledge for the course, and what one would need for second part. And you see the energies here are the same offset. Okay, I think we are done with lecture 2, and there is no time to start another thing. I'll just bring what. So when we meet on another, oh, it will be in 2 weeks, right? Next Monday you present. On Wednesdays we do labs. So in 2 weeks we'll go over operators, concept of the eigenstates. We'll just go over it once again, and there will be what else we need to cover. And we need a key thing for your projects. So the ways to predict future. So in one of the narrow senses, quantum theory is a way to predict future, which should be interpreted as a way to say what will be the wave function of a system in the next instant of time. And as soon as we cover this concept, we will be ready to do projects. Okay, I think we are over time. So meeting is done. Everyone is welcome to disconnect and depart. If there are any questions, I'll stay here and answer. I need to collect your votes. And are you done? And also collect your spectra. Oh, you still. Thank you. Just quickly do things here. Draw spectrum here. Still working? Yes. So those are already here, right?
Yes, so those are here. So then this matching up with my exact number?
So
My exact value, or do you want to use a number?
no, exact numbers.
Okay.
And select the biggest one, like 0.20 is your biggest. Then instead of doing from 0 to like 0.20 here, so that you use the space wisely. Okay, yeah, please send me a reminder by email.
Lola, which one do you want the least?
Thank you. Have a nice day. Good, good.